So Einstein decides that in the photoelectric effect, light is not acting like a wave. What is it acting like? So here are our pebbles on the beach. And we want to consider what kind of thing, when we have a huge amplitude, still does not disturb the pebbles on the beach. What if you have things that are just tons of it, it still won't disturb the pebbles on the beach? And the thing that won't disturb, if you have ping pong balls. Ping pong balls. You throw ping pong balls at the pebble on the beach, and the pebbles don't go flying away. Doesn't matter how many pebbles you are putting on, ping pong balls are putting on, it's not going to eject the pebbles. So Einstein decides that when u is less than u0, that's at the left in the graph on top, in the dotted line region, u is less than u0, light is acting like ping pong balls. So here's the graph. Ping pong balls in this region. And then, what about if you try bowling balls? Well, if you throw bowling balls at pebbles on the beach, the pebbles go flying away. And you say, oh, I want to have fewer, I don't want to have the pebbles going away. I'm going to throw fewer bowling balls. So you decide to throw one bowling ball every 5 hours. It doesn't matter. Every time you throw a bowling ball, some pebbles are going to go flying away. And so that's the situation where nu is greater than u0. It doesn't matter how few of those you have. You always eject some electrons. And so this region here is the bowling ball region. And so Einstein's decided that the frequency connects to what kind of ball you have. The light connects to what kind of ball you have. Einstein concludes that based on the photoelectron, that in the photoelectron experiment, light is acting like a ball. Light is acting, well, we don't call them balls, is acting like a particle. So, light is not just a wave with a frequency and a lambda, but in certain circumstances, it acts like a particle. That's what happens in the photoelectron experiment. And Einstein does lots of stuff. He figures out a theory called special relativity. Special relativity is the theory of things that are moving very fast, velocity near c. And he discovers that in that region, Ek is not equal to 1/2 mv squared. And momentum is not equal to mv. When things are moving near the speed of light. Of course, Ek for light is equal to h nu. That's the Planck relation. And he finds out what Ek and how kinetic energy and momentum are related in general in the theory of special relativity. Ek squared equals momentum squared times the speed of light squared plus m0, and I'll explain what m0 is in a second, squared times the speed of light to the 4th power. m0 is the rest mass. The rest mass is how much a particle weighs if you're right on top of the particle. And light has m0 equal to 0. It has no rest mass. And so Einstein then can just plug this in. Ek equals h squared equals h squared nu squared from Planck's relationship. I can drop the m0 term, so it equals p squared c squared. That means that h nu equals pc. P is equal to h nu over c. C is the speed, and that's always the frequency times the lambda. So the two frequencies pass out, and he gets the key relation that P equals h over lambda, also written as lambda equals h over P. Okay, so this is what Einstein has discovered. And what do we have for you here? Here's a picture of Einstein with Planck, and Planck is at the piano, and it shows their human side. And one thing about the human side is about their scientists are humans. We interact with them, and thinking about this, I'm very much drawn to the fact that a story my father told me. My father told me that when he was a young physicist, Einstein asked to see him. It was 1952. He, together with another physicist, C.N. Yang, wrote a paper on phase transitions, and they got a letter from Einstein saying he wanted to see them. And so my father was just a few years older than you, and he and C.N. Yang go to see Einstein, and of course they're in awe to see the man. And Einstein asked them to talk about their paper, and the paper is in a field called statistical mechanics, and Einstein is one of the founders of the field of statistical mechanics. And they start talking about the paper, and they use something called the Grand Canonical Ensemble. Well, that sounds fancy, but the Grand Canonical Ensemble must have been invented in the 20s or 30s. It's really old. And they discovered to their astonishment that Einstein has never heard of it. And in there you see the triumph and the tragedy of Einstein. Because Einstein was a great scientist, a great physicist, and for 20 years, so much of everything that happened in physics just came out of his brain. But eventually people absorbed his ideas, and they had their own ideas. And Einstein was a recluse. For my father and C.N. Yang to be invited to see Einstein was extraordinarily rare. And because he was a recluse, he didn't go to talks, he didn't hear other physicists speak. And eventually he had no idea what was going on in the world of physics. And so a field that he created, the important results that came a few years after him, he was unaware of them. And the message for you is, as the future scientists of America, science is done with other people. Even if you're Einstein, you cannot work alone. Okay. So now, here is the relationship. Light is acting both as a wave and as a particle. It has a lambda. It has a frequency, and key relationships are like the one I just showed you, these two here. And then what's the next step of the story? The next step of the story is, if light is a wave and acting as a particle, maybe particles are not just particles, they act as waves. And we get to the important relationship, the Broglie equation, proposed by de Broglie, which is that electrons might have wavelengths. And these wavelengths might obey the rule lambda equals h over p. Here's a picture of de Broglie. So that's the de Broglie equation, lambda equals h over p. Here's a picture of him. There he is on the right. Oh, and one thing. This is not the real way you pronounce the guy's name. In French, the G, the L, the I, and the E are silent. So his name is, well, say it. So what do you think his name is? You might come up with a name like de Bro, which is way closer than de Broglie. So de Broglie, and this is a picture of him. There he is on the right with his great-great-great-grandfather. And the amazing thing about this picture is, look at the resemblance. Look at those two people. Maybe I can make it bigger. Can you see how they resemble each other? Look at their nose. Write in chat what other parts of the body, the face they share. What I think is the eyebrows. Look at those eyebrows. Anyhow, de Broglie creates the relation lambda equals h over p, and then this is later confirmed that electrons have a wavelength by this result. By Davison and Gerner, they discover, you see that pattern, the intense, the zero, the intense, the zero? That's diffraction. They discover that electrons diffract. Electrons are actually waves. This is the particle-wave duality. Electrons are particles and waves. Light is a wave and a particle.